So CrystalNet is a web application that we've developed that you can find online on our group server, and that's based on an algorithm implemented and developed by Lionel Zubritsky, a PhD student in my group, which we've described in a paper posted on SciPost Chemistry, and I'll give all the links in the description. So the goal of this CrystalNet was to create an open source implementation of a library to identify topology in crystalline materials. And this was implemented in Julia. And the main goal was to document well the algorithm, the choices made to identify unique topology identifiers, and to benchmark the implementation against different crystal databases. And we found that compared to the other solutions available, such as the two implementation of Sistre in JavaScript and Java, CrystalNet actually performs, because it's implemented in Julia and because Lionel has heavily optimized it, it actually performs very fast for the identification of most systems, under a second for most of the crystals that we've been trying it on. And so we figured out we could make a web app version of it so that it's easier for people to use without installing Julia, without knowing how to program in Julia, etc. So the interface is like this, and you can actually already see how it works. You have a drop zone to upload a file. You have very different options below, and you have a lot. Actually, we won't be discussing them here. They're all detailed in the papers, in the documentation. There's a manual as well that describes everything here. So the entire power of this library is available, but we've made some default options that should work out well for most of the files. In fact, let's try it right now. And so we take a simple MOV structure. I have a hcust1 file available. Just default everything, bonding, structure type. Let the software do its magic, and you will see it identifies hcust1 as a TBO topology, and it shows you here the visualization of both the CrystalNet and the topology. So you can actually zoom, rotate, figure out where your typical hcust1 is. You can decide to display or not display the subnet so you can see it better. Okay, so this is actually an easy case. Everything works great. Whatever the type of clustering that you choose, the structure is well identified as a TBO. You can even open it on the RCSR, so Reticular Chemistry Structural Database, find more information, find other systems, reference other systems that use this topology, etc. Nice picture as well, visualization of the tiling, all there is to see. Going back there, we can have sometimes CIF files with a bit more mess in them. I upload this one, which is a structure with solvent in it, and as you can see, it still finds a TBO topology, but there are warnings, and the website tells you that there are some warnings. Now, in most cases, they're not actually a problem. Just want to highlight what type of warning you can find. So the first one is that I actually uploaded a CIF file that did not have bonds inside, and so the algorithm actually took a guess at what the bonding pattern is based on atomic, ionic radii, etc. And so it warns you about that. If you really want to have no heuristics used, then you should provide a CIF file with bonds. Some of them do. Also, it tells me that it found what is possibly solvent residues that are structures inside the CIF file that have dimension 0, so they're not periodic. In this case, I can check, and they were actually, I could check the CIF file, they were actually solvent molecules. In fact, some of the water molecules bound, and so that's fine because that's how I want it. But whenever that happens, it's always good to have a check. So these are the typical warnings, like the most common one you will see. we can look at other MOFs. An interesting one is MOF 14, which I have available here. So if you look at MOF 14, you will see that it actually tells you that it's an interpenetrated network. It has two substructures. They're both PTO. You can zoom around, have a look. You can actually toggle on and off the display of the different substructures if you want. Just see what's happening one and then the other. So that's actually quite useful to understand, to visualize the type of interpenetration there is. And so they could possibly have different topologies, but in this case, they actually have PTO topology. There are warnings as well. They're actually usually the same, so there were bonds in the initial files, but they were weird, not consistent with the chemical rules within CrystalNets, so it decided to actually remove them. If you don't like that, if you want it, force it to keep the bonds that were provided on input, you can do this here. Instead of auto bonding, you can say, just use whatever is in input. In this case, would give the same result, but always best to check. Trying another file, we can even push it to very big systems. So MIL 101 has like 14,000 atoms in the unit cell. You will see it takes a bit longer in this case, actually uploading a few seconds, handling it a few seconds. Visualization, well, that depends on your, basically my laptop is kind of new, so it works well, but can be a bit slow. Lots of atoms. Let's say I just want to look at that network. So it's MTNE network topology. Look how beautiful it is. Really lovely. So yeah, we can handle relatively large structures. In this case also, you will see that I didn't have to specify anything. I could have actually helped the software by telling it already, it's a MOF in the determination of the bonding patterns. It helps a bit. Instead of guessing, if you tell it already it's a MOF, it will allow for some kind of looser metal, metal oxygen, metal nitrogen distances as bonds, rather than when it thinks it's an inorganic. So anyway, I could have told it it's a MOF, but I didn't. It did figure it out. I can play with other things. MIL 47 is a nice example. You'll see. I'm gonna tell it's a MOF. It doesn't change much, and I'm also leaving the clustering as is default on auto. And you will see there that it provides there are two different clusterings, all node and single nodes, that you can find. That they have different topology depending on how you define the clustering. So it's this typical wine rack framework. Okay, but in the other direction, if you look at, this is actually the visualization for the all nodes. So this, if you switch to the single nodes, you'll see that it shows here a different representation, a different clustering, where basically the core of your linker is one node, one vertex, and the metals are others. And so depending on what you've chosen as a clustering, you get either RNA topology, which again we can see the wine rack there, or BPQ, which is a different topology for this single node clustering. Continuing there, trying this time a zeolite. Actually, will not tell it it's the zeolite. I will guess it. Let it guess. Actually, a big one with an interrupted framework. The ITV zeolite. Well, it works the same basically. You can see the framework. Actually, in this case, of course, each vertex is a silicon atom, so the structure is really very close to the zeolite structure itself. And you can apply it to other things. So bigger systems with zeolitic topology are like this ZIF64, which has a zeolitic topology, but in a hybrid metal inorganic realization. In fact, if you look at the topology there, it gives you two codes, because this structure has a name in the reticular chemistry structural database, which is different from the typical three-letter code from the International Zeolite Association. So it actually gives you both names. So in the RCSR, it's a CRB structure, and in the zeolite world, it's known as BCT, capital letters. Okay, so that's for zeolites, but you can actually apply it also to oxide systems or other inorganics. In this case, a wurtzite form of ZNS. It will actually, this framework's quite beautiful. It's Lonsdale-like topology. Again, so it works across a large range of systems. We've used it and tested it a lot on zeolites, aluminophosphates, and metal organic frameworks, but it's quite a general framework to identify topology of crystalline materials. Anyway, this was the short presentation. I hope you like it. Can try it online. Ask on Twitter, by email, if you have any questions. See you around.